Good day, class. I remain your favorite tutor, Adeyeye Adeolu, teacher. Okay? Now, today we want to look at the energy of simple harmonic motion. Energy of simple harmonic motion. And I'm going to use two different diagrams to explain this. Two different diagrams. The first one is the simple pendulum bulb, while the other one is a loaded spiral spring. So let's look at the first one. If this is a rigid support, please, for you to understand this topic, you must have watched my first two videos on simple harmonic motion. This is the concluding part, please. This is the concluding part. And this one is a rope. That's a string. Then with a bulb here at the equilibrium position, C. So if you displace it to point A and you release it, it will oscillate about the equilibrium position. Then it will come to point B, so that the path of the motion of the object is going to be this. This is the path. Now, point A and point B, let me call it point B. Point A and B are the maximum what? The maximum height of the bulb. Point C is the equilibrium position. If you have watched my first two videos, you must have seen that there. Okay? Now, according to the principle of conservation of energy, I've also dropped a video on the principle of conservation of energy. Please go and watch it to understand this one better. The principle of conservation of energy says that energy can neither be created nor what? Nor destroyed. They can be transformed from one form to another. That's in a closed system. Let me repeat. In a closed system, energy can neither be created nor what? Nor destroyed. They can be transformed from one form to another. Now, what is the energy they are talking about here? Because this bulb, as it's moving to and fro about the equilibrium position C, the energy it has two energy, and the energy is going to be changing from one form to what? To another. So who can tell me what the energy here is? The total energy here is what? Is potential, because at this point it has not started moving. So we have PE max here. PE max at point A, and that PE max is equal to mg what? H what? H max. So what do I mean by H max? If I draw a horizontal line here, draw another horizontal line from where the bulb is here. So it means the bulb has been raised from here to here through this what? Through this particular height. So this is my H what? H max. This is the maximum height of the bulb. You can see now. From here like this. From here to here, from here to here. It's the same thing. So that's the maximum height. So when an object is at a particular height from a reference point, so this is our reference point. So when it is here, it is at this height. All right? So when an object is at a height from a reference point, it possesses what? Potential energy. And the same thing is applicable at point B. At point B, the only energy, because the bulb will swing through C to what? To B. So the only energy here is PE, which is mgh what? Max. So we have maximum potential energy at both points A and what? And B. But now, the moment the object begins to move, what happens? The potential energy will begin to what? To reduce. For example, you can't expect the potential energy here to still be equal to the one here. It's not possible. So the potential energy at this point, let me call it point D. At point D, PE is also equal to what? mgh. But this H is not up to what? To this maximum what? Maximum height. So it means this PE here is what? Is less than PE what? PE max. But there's another energy that we have here. What is the energy we have there? That's what? That is kinetic energy. But let me assume that this height here. Let me assume that this height here, H. Let me assume this is let me use 6 centimeter. And let me assume that H max the height here, let me assume is 10 centimeter. 10 centimeter is 0. What? 0.1 meter. Then 6 centimeter is 0.06 meter. So, okay, can we calculate? What's the mass? Let me assume the mass to be 0.5 kg. 0.5 kg. So who can tell me the potential energy here? So the potential energy at E, which is PE max, will now be equal to mgh what? Max. I want to prove something to us. So what's the mass there? 0.5 times, assuming G to be equal to 10 meter per second square. So that's times 10 times what again? What is the H max? 0.1. So if I calculate this, what do I have? I have 0.5 what? Joule. 0.5. Is that 0.5? 0.5 times 10 times 0.1. Yes, that's 0.5 joule. Okay? Now, who can tell us what the kinetic energy here is at the maximum height? The kinetic energy at maximum height is what? Is 0 joule. Now, why is it 0? Why is kinetic energy here 0? The reason is because at maximum height, there is no velocity. Velocity is equal to 0. So because V at this point, V equals what? 0. So that's why there's no kinetic energy, because kinetic energy is a function of the mass and the velocity of the body or of the object. But as the object is coming down, what happens? Velocity is what? Is now increasing. So from 0, it begins to rise. It begins to rise until it gets to the center, where it becomes what? Maximum. So at the center here, what do you think the energy is going to be? Total energy. Total energy is still what? Is still the same thing. But let me continue my proof. Now at point D, what is our height? Our height from the ground is what? Is 0.06. Well, now let's calculate the PE there. PE at what? At D will now be equal to mgh. What's my mass? 0.5. What's G? 10. What's H? 0.06. So let's calculate that and see what we're going to get. 0.5 times 10 times 0.06. That's 0.3. 0.3 joule. So the PE here is 0. What? 3 joule. So please, who can suggest what the kinetic energy here is going to be? The kinetic energy here is going to be what? Your guess is as good as mine. That's 0.5 minus 0.3, which is what? 0.2 joule. But what is the proof for that? Can we prove that? Okay, let's prove that. Let's get our velocity here. What do you think our velocity here is going to be? We use V square equals what? U square plus 2G what? 2GH. V square equals to 0 square. Now, the object is falling from here to here. So we are going to consider the object falling freely under what? Under gravity, from the knowledge of projectile. So initial velocity here is what? 0. So let's say U now. U now, instead of saying V, we use U. U equals 0. Now by the time it falls from here to here, please don't forget that the height, this 6 centimeter, is from here to here. It's from here what? From here to here, not from here to here. We need to get the height from the vertical height from this point to what? To this point here, which is here to here now. This is going to be what? That's 10 minus what? Minus 6. That's 4 centimeter, which is now 0.04. So our height is 0.04 meter. So let's calculate that. That's times what? Times 10 times 0.04. So V square is going to be equal to, that's 20 times 0.04. That's what? 0.8. And V be equal to square root of 0.8. Or let's leave it this way. Now what's our KE? Our KE at point D. KE will now be equal to what? Half mv square. Potential energy. Kinetic energy. The energy possessed by a body by the virtue of is what? Its motion. That's half times, what's the mass? 0.5 times 0.8. So 0.8 times 0.5 times 0.5. That's what? 0.2 joule. So we can see now our PE here is what? 0.3. Our KE is what? 0.2. So if you add the two together, KE plus what? PE will now be 0.2 plus 0.3, and that's what? 0.5 joule. So you can see that the energy here is also equal to the what? To the energy here. It should also be equal to what? To the energy here. But the only energy here is what? Do we have any potential here? No. So PE at the center here is what? 0. But what of KE at the center? Now at the center, that is where we are going to have maximum what? Velocity. And since we have maximum velocity, we now have maximum what? KE, which is now half mv square max. Okay. So why is PE equal to 0? Because h at h is equal to what? 0 at point C. There's no height from, because this is our reference point. Our reference point is this center C. So since we have no height, since the ball has not been raised to any height from here, so the potential energy is going to be equal to what? 0. While the kinetic energy is now going to be equal to half times 0.5 times. So let's find our height here. So by the time the ball travels from here to here, it has traveled through what height? Through 10 centimeters, which is 0.1 meter. So let's calculate the velocity again. At the center, v square equals u square plus 2gh. That's 0 initial velocity. Your object is falling freely. Plus 2 times 10 times 0.1. So that v square will now give us what? V square is 2 joule. Now, let's calculate KE. Sorry, not 2 joule. 2 meters per second, I mean. So KE will now be half times m times what? V square, which is now half times, what's the mass again? That's 0.5 times, what's our V square? 2. So this cancels this. What do you have there? 0.5 joule. So you can see that the energy here is what? Is 0.5. That's PE plus KE. Gives us what? 0.5 joule. So that is what happens at any other point. At any other point. So that the energy is what? Is constant. So if you have 0.5 joule here, only PE, KE is 0. So the total energy you will still have here is what? 0.5. Both PE and what? And KE all together. Now here, total energy is still what? 0.5. Only KE. PE is what? 0. Total energy here is what? 0.5. Here, 0.5. What of here? 0.5. Anywhere you get to, the energy remains the same. That is the proof of the principle of conservation of energy. So in exams, at times they may ask you to draw a pendulum bulb and shows how the energy fluctuates. How the energies fluctuate. The changes in energy along the path of the bulb. So here, PE is what? Is maximum, which is equal to what? mgh max. But KE is what? 0. Why here? Here, PE is what? 0. And KE is what? Maximum, which is half mv square max. This is where we have maximum velocity at point C. Then here too, we have PE max, right? mgh. Then KE at point B is what? 0. So at the extreme ends, KE will be 0, PE will be maximum. At the center, PE will be what? 0. And KE will be what? Maximum. Then at every other point, let me say point D, let me say point E, we have both PE plus what? KE, which will now be equal to what? mgh. Don't forget that this h is smaller than the maximum height. Then plus what? Half mv square. Don't forget also that this v is smaller than the what? Maximum velocity. So that according to the principle of conservation of energy, total energy is constant. So total energy, which is the energy at what? At A equals what? Energy at what? At B also equal to what? Energy at what? At C, right? Also equal to what? Energy at what? At D. At any point, the energy must be the same thing, although it is changing from one form to another. So potential is reducing, While kinetic is what? Is increasing. So kinetic becomes maximum here, potential becomes what? 0. And as you are going up again, potential is what? Is increasing, while kinetic is what? Is reducing. So that kinetic becomes 0 here again, and potential becomes what? Maximum. So the same thing happens again and again periodically. Okay? So what's the energy at A? The energy at A is what? mgh max then equals, I don't need to write energy at B because it's still the same thing. K is 0, so I don't need to write half mv squared. Then it's equal to what? Energy at D. What's energy at D? mgh plus what? Half mv squared. This energy at A, this energy at D, then equals energy at what? At C, which is half m. Let me shift it on, please. Energy at A is mgh max. Then energy at D, mgh plus half mv squared, then equals energy at what? C, half mv squared max. So you can equate any of this to each other. So I want to equate these two together. Energy at A and at C, which is now going to be mgh max equals what? Half mv squared max. So this mass can cancel each other. Now, if you cross multiply, you have 2gh mass equals to what? V square max. And if you make V the solid formula, V mass will be equal to square root of what? 2gh max. So this is maximum velocity. This is the relationship between maximum velocity and maximum height. So let me give one example. Just one example. A bulb of mass 0.2 kg is raised to a height 8 centimeter from the equilibrium position and released to oscillate freely. Calculate figure 1 the maximum PE. Figure 2 the maximum KE. Figure 3 the KE, the PE, and the velocity at, let me say, 5 centimeter from the equilibrium position. So let's tackle these questions. Are we following? Please follow me. Solution. So the mass of the bulb, a bulb of mass 0.2 kg. So mass equals 0.2 kg. Let's interpret what we have there. Then it's raised to a height 8 centimeter. So maximum height is what? 8 centimeter. Convert to meter. So we have something like this. Okay. So this A, this B, and this what? This C. So it means this height from here to here is 8 centimeter, which is 0.08 meter. So it's been released from there. So what's the maximum PE class? PE max will be equal to what? mg age max. Take G to be equal to 10 meter per second square. So mg age max. So what's our mass? Our mass is 0.2, G is 10, age is 0.08. So 0.2 times 10 times 0.08 0.16 joule. That's one. Then number two, the maximum KE. Do we need to calculate maximum KE? Yes or no? There's no need. Just say according to the principle of conservation of energy, maximum PE, which is energy here, we go to maximum what? KE, which is energy what? Here. So maximum KE equals what? It's also equal to what? Maximum what? Maximum PE, which will now be equal to 0.16 joule. There's no need calculating at all. Then number three, you can see how important it is for you to understand the law and not just cram. Number three, the KE, the PE, and the velocity at a 0.5 centimeter from the equilibrium position. Now, 5 centimeter from the equilibrium position, maybe let me say around here, at a height 5 centimeter. So this is 5 centimeter, which is 0.05 meter. So this time around, our height is 0.05 meter. So I think we can calculate the PE first. So what's the PE? PE equals mgh. What's my mass? Mass is 0.2. G is 10. H is what? 0.05. So what's that one going to give us? So we are 0.2 times 10 times 0.05. That's 0.1. So class, what do you think the KE is going to be? Just apply the principle of conservation of what? Of energy. Example, let me call here point D. The total energy here is both potential and what? And kinetic. So meaning PE plus what? KE. Now, the PE plus KE, what do you think is supposed to give us? It's supposed to give us the total energy of the system, which is what? 0.16. But now, we already know the PE at that same point, at the same point. What's the PE there? That is what we just calculated now, 0.1. So let's substitute 0.1 then plus what? KE. KE is what we are looking for. Then equals 0.1 what? 16. So make KE the solid formula, 0.16 minus 0.1. And that's what? That's 0.06 joule. So that's our KE there. But the last one says the what? The velocity. So just do this. Just do this to get the velocity. KE equals what? Half mv squared. Now, do you know our KE already? Yes. So we substitute 0.06 equals half times what's our mass? 0.2. Then times what? V squared. If you cross multiply, you have 2 times 0.06 equals 0.2 v squared. Then this one gives us 0.12 equals 0.2 v squared. So that v squared will now be 0.12 over 0.2, and that's 0.6. Then what's v? Square root of 0.6, and that's what? Square root of 0.6. 0.7746 meter per second. So that's the answer there. So that's it. Now, that's that for simple pendulum. What if I'm to do the one for a loaded spiral spring? A loaded spiral spring. Now, for a loaded spiral spring, you will need the knowledge of Hooke's law. You must have done Hooke's law in your junior classes. I mean your SS1. You must have done Hooke's law. Hooke's law of elasticity, which says that provided that the elastic limit, right, of what? of an elastic material is not exceeded, the extension E is directly proportional to what? To the force applied or to the load on that particular elastic material. For example, is a spiral spring. Okay. Now, for a spiral spring, I'm going to draw three different diagrams. The first diagram, I will show us the unextended length of the spring. This is that's when the spring has not been loaded at all. No load has been placed on it. So this is original length, L naught. L naught. Now, it is from the unextended length. Okay. Unextended length first. Okay, we can't get the first constant from here. Then this, let me call this one figure 1.0. Then I will draw another one. This is when we now have a mass, a load hanging on it. Hanging. And when a load is suspended at the base of the what? Or the spiral spring, what happens? There's going to be an extension. It will draw it down. So it's no longer be the way it is here. So it's going to extend downward because there is a load here of mass what? Mass M. So you should draw it downward this way. So that we now have a new length. Now let's check from here to here now. Now, the new length is from here to what? To here. From here to here. Or let me do it this way. Let me say from here to here. So this is the new length, which is our extension now. This is the extension. Sorry, that's not even the new length. The new length is from here to what? To here. That's the original length plus what? The extension. Now from here we can calculate what we call our force constant. This is the mass. And the weight or the force from this mass is going to be equal to what? M what? Mg. F equals mg. There is something that is called the force constant of an elastic material, for example, of a spiral spring. The force constant is also known as the stiffness. So, F equals to what? K what? Ke. F equals Ke. Where K is now the force what? Constant. E is our extension or compression in meter. This is our force in Newton. Force in Newton. This one is our extension or compression. In the case of compression, if it's being compressed, in what? In meter. So K, that's I'm just revising Hooke's law with us. K is going to be equal to F over what? Over E. And the unit is going to be Newton per what? Per meter. Now, please, for your information, when this load is suspended and it helps stretch the spring by an extension E. Now, this is now going to be the new position of the what? Of the spring, this point. We now have an equilibrium position. So, this place there, this level here is what? Is our equilibrium, the new position of the spring is our equilibrium what? Position. When you are dealing with simple harmonic motion, you must always have the equilibrium what? Position. Now, at this position again, I'll now use my own force to draw down, just like when you displace a pendulum bob. When you displace it, you use your own force to displace it. Now, it is not my own force I use to displace this. It is the mass I place on it. Then the force that is now being introduced by that mass is this F now. F equals what? Ke, which we will now use to find the force constant, the stiffness of what? Of the spring. So F equals Ke. This is the force as a result of this what? As a result of this mass. That force is also known as what? Load. You have already loaded the spring. But when you loaded this spring and you remove your hand, you allow this mass to be hanging, there's no oscillation. There's no what? There's no oscillation. As far as you didn't draw it with your own hand, you just allow the mass to be suspended freely, and you remove your hand, there's no oscillation. So at that point, what we have is what is equilibrium position. So the mass remains there, just like this bulb remains in position like this. Look at this bulb, just like this bulb here remains in what? In position. This bulb remains in position here. It remains in position. This is the equilibrium position. So for this one, this is the what? Equilibrium position. Now you now introduce your own force. By the time you introduce your own force and you draw downward, you put your hand on the mass and you draw downward. We now have another diagram. It's now going to extend the more. It will extend the more. So that this the new position now. Now this equilibrium position, I will draw it to this point. Okay. So we now have an extension again. Then that extension, I'm going to call it Y. I'm going to call it Y. Now, from here to here now becomes Y. And this Y now is what? Is equal to A. That's maximum what? Displacement from the equilibrium position. And what do we call that? Amplitude. So we call it amplitude. So this is our amplitude now. Maximum displacement from the equilibrium position. So I displace it here and then I will release it. I use my own hand to pull it down and then release. When I release it, what happens? This mass now begins to what? To oscillate to and what? And fro about the equilibrium what? Position. What do I mean by to and fro? It will go up and what? And come back. So let me assume the maximum point it reaches here is what? Point what? Point B here. So let me call here point A. Yes, point A. Point A. Please don't mix this A with here. This one is distance, amplitude. Why? Yes, point what? Point B. So I will call here point what? Point what? The equilibrium position is point what? Point C. The same letter we have been using since. Okay. So it oscillates about point C, goes up. So from here to here is toe. From A to B is toe. Then back from B to what? To A is what? Is fro. So that makes a complete oscillation. From A to B is half oscillation. Then from B back to A is what? Half oscillation. So from A to B back from B to A is now complete what? Oscillation. Are you following? So maybe from A to C is 1/4. C to B 1/4. B to C 1/4. C to A 1/4 of a full oscillation. Okay. Now we are going to follow the same principle of conservation of energy, the law of conservation of energy. I will do the same thing here. So what is total energy here when the thing is being displaced? Total energy of the bulb, yeah, that is as in the mass, the energy of the mass here. Total energy here is what? PE. We have PE max here. PE max. And what is PE max? Now, please, for information, we are going to be using something different from the pendulum bulb. We are not using MGH here because we are dealing with a spiral spring now. There is potential energy that is stored in any elastic material that is being stretched. If you stretch a rubber band, if you stretch a catapult, there is potential energy being stored in them because of their elasticity. So it is the energy that is stored, the potential energy that is stored in a catapult that you release to help you kill a bird. Okay, so this is it. For an elastic material, what is the energy stored? Don't forget that energy and work, they are used interchangeably because both of them have the same unit. Both of them are measured in what? In joule. And energy is stored in an elastic material is equal to average force times what? Times the extension produced. Average force times the extension produced. Now what's the force? F. That's going to be half times what? F. Then what's the extension? E. So which is now half what? Fe. But what is F? The F is the force that is causing the extension, and that F is equal to what? K what? Ke. So if I substitute here now, I will now have energy to be equal to half times, what is F? Ke. Then times what again? Times E. Only this one is what? Is F. So if I simplify, I will have, I'm going to have half what? Times Ke square. Half Ke square. But this time around, what is my extension from the equilibrium position? My new extension, my new displacement is what? Is A. So it means my potential energy here will now be half K A what? A square. Please take note of this derivation. Half K A square. Now you can tell us what the kinetic energy is going to be here. Ke here also is going to be equal to what? It's going to be equal to 0. So from here down here is the maximum displacement downward, maximum downward displacement. Then from here upward, by the time this spring compresses up, it will get to a point again where it will no longer be able to compress again. Then from there it what? You start coming down again. So that's how oscillation is going to what? To continue. So at point B, PE is also maximum here. That's what? Half K A square. Then KE is what? KE is what? 0. Because there's no velocity. It's from here that it's now begin to what? To fall freely again. Under what? Under gravity. Now, what do you have again? At point C, which is the center of oscillation, just like what we have for simple pendulum, we are going to have maximum what? Kinetic energy. So we have Ke max, Ke max, which is what? Half mv square max. But what is our PE? There's no displacement now. So PE is what? Guess what it's going to be? That's what? 0. I'm not done. So point A, the energy at point A, energy at point B, they are the same thing, only PE. Energy at point C is what? Is Ke. But for your information, according to the principle of conservation of energy, energy here at A is equal to energy at what? At C. Total energy at C is equal to total energy at B, equals to energy at B, yes. And it's also equal to the total energy at what? At A. Energy at any point along the path of the motion is what? Is constant according to the principle of conservation of energy. Now, let me pick another point. Let me pick here point D. So, or let me pick down here. Let me call here point D. Now, at point D, what do you think the energy is going to be? We are going to have both PE plus what? Plus Ke, because there's both displacement and there's what? Velocity at point A, because the thing will still be going up or coming down. So there's velocity and there's what? There's height, there's displacement. But what is the PE here? The PE at point D is going to be what? Half K. Now, this time around we are not using A because we don't have maximum displacement here. So we have ordinary what? Ordinary Y. Half Ky what? Y square. Then what is the kinetic energy? Ordinary half mv square, not V max this time around. It's only here we have V max. At point C, we have maximum velocity. So at point D now, we have ordinary velocity. It can be up to the velocity at what? At C. So we have half Ky square plus half mv square. Now, I still want to write another equation out from here. That's the reason for all this explanation. So that according to the principle of conservation of energy, energy at A again, at A equals to energy E at what? Energy at what? At C, then equals energy at what? At D. You can also pick any other point from here to here. Any other point, you can pick here, you can pick here. Energy here is energy here, 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 is energy here at any other point. So what is energy at A? Only PE. Half K A square. What's the energy at C? Only Ke. Half mv square max. Don't forget that A is maximum what? Displacement. And what's maximum displacement? That's what? Amplitude. Measured in what? In meter. Then what's energy at D? Energy at D is half Ky square potential plus kinetic. That's what? Half mv square. Okay? So from this equation, I can equate any of these equations again, just like I've been doing before. Okay? Okay, so let me equate half Ka square. I want to get a formula out from here again. Let me equate energy at A to energy at D. What will I have? I'm going to have half Ka square equals half Ky square plus what now? Half mv square. I'm equating this to this. So collecting at like terms, the two potential energies, bring them together. So we are going to have half Ka square minus half Ky square equals half mv square. Correct, factorize there. That's half. What's common to them? Half and what? And k. So half k, then what do you have inside? A square minus y square equals half mv square. So half can cancel half here. So what are we left with? K into a square minus y square equals mv square. Make v the subject of formula. So if you do that, we are going to have k into a square minus y square all over what? M equals to v square. So rearrange. V square be equal to k. This is written as k over what? Over m into what? A square minus y square. Okay? Now please look at this formula very well. This formula is looking like something that we have done before. My first and second video. If you check my first and second video, you notice that this formula looks like something there. What does it look like? This formula is looking like V equals to omega root what? A square minus what? S square. Can you recollect? V equals to omega root A square minus S square. But this time around, instead of x, because x is displacement, just like y is also what? Displacement. So we use y square. In fact, sometimes we use y instead of x. So let's complete what we are doing here. Find the square root of both sides. We have v now to be equal to square root of what? K over m into what? A square minus y square. Please write this one somewhere. This one. Then, if I break it down, I will have root what? K over what? Over m times what? Times root what? A square minus what? Y square. Yeah, let's compare. Now let's compare. Let's compare these two. Let's compare now. Let's compare this formula and v equals to omega root times root A square minus y square. So who can tell me what the implication is? What does this one mean? If you compare the two, this v is this v. This root A square minus y square is this. Now, this one is multiplying this. This one also is multiplying this. And these are the same thing. These are the same thing. So what does that mean? It means omega itself, omega is equal to what? Root what? K over what? Over m. Root K over m. I'm not done. Let me call this one equation 1. Equation 1. So what is omega? Omega is angular what? Angular speed in radian per what? Per second. What is K? K is our force constant of the spring. Force constant of the spring in Newton per what? Per meter. What is M? M is the mass of the spring, spiral spring. Now I'm not done with this formulas. I'm not done. If I move on, do you remember what omega is again in our previous videos? You remember? Recall that omega, recall recall that omega is equal to what? 2 pi f. Or omega equals to 2 pi over what? Over t. Now let's substitute into equation 1. So so that is a 2 pi f now is equal to what? Root k over m, where f, if you divide both sides by 2 pi, f will now be equal to what? 1 over 2 pi root what? K over what? Over m. Call this one equation what? 2. Right? Okay. I want to express this again in terms of what? In terms of period. What is f again? F is what? Since f is equal to 1 over t, right? It means 1 over t will now be equal to 1 over 2 pi root what? K over what? Over m. If you make t the subject of formula, if you make t, now what is t? The period. What is f? Frequency. Okay? Make t the subject of formula again. If you simplify this, making t the subject of formula, t will now be equal to 2 pi root what? Is that around? That's m over what? M over k. Now let me call this one equation 3. Where m is the mass, this mass here, this load here, and k is the first constant of what? Of the spring. T is the period in what? In seconds. Now I want us to compare these two formulas. There's a formula that looks like this. I think in my second video on simple harmonic motion. That formula says T equals to 2 pi root what? L over G. Now you know the reason why I'm doing this. If you can know this formula very well, you'll be able to know this and what and this offhand without cramming. Because in the exam, some students, in fact many students, they mix these things up. They can say F equals to 1 over 2 pi root M over K instead of K over M. And this one they can say T equals to 2 pi root what? K over M. But how you do that, you not mix it up. Once you know this one offhand, you know, look at this, so they look alike, right? Okay, so T is 2 pi root what? L over G. G is our length, upon which T, the period, depends. If you can remember what we did the other time. So T depends on what? The period depends on the length of the spring, right? Of the string, I mean. Then this G is what? Is constant. Acceleration due to what? To gravity. So this G is constant. Now compared to this one too, it means the period also depends on what? This one around? On what? On mass, on the mass. Then this one is again is what? Is what? Our what? Spring what? Constant. So don't forget that it's constant that will always be below. Constant will always be below. Why for here mass is up. Here what is up? L. So if you can know this one for period, you should be able to know which one you are going to reverse here for frequency. This time around for frequency, you know, period to period, you compare period to period. Then for frequency, what happens? Constant goes up, mass comes down, then 2 pi also what? Comes down. So please take note of that. Very important. So I think I'm going to end the class here. I will drop another video which has to do with different examples. So there I'm going to be solving miscellaneous exercise, several exercise from all we have done so far. So that is all about the energy of simple harmonic motion. Please subscribe to my channel, like, comment, and share with your friends so that they can benefit also. Thank you.